Welcome back. This is our first chapter 2 video all about relations and functions. By the end of this, we will be able to analyze relations and functions and use equations of relations and functions. This video is pretty concept heavy. So here's our first concept. So you have this printed for you if you're following along with my guided notes. There are different ways that we can categorize functions. One of those ways is having to do with the idea of being one-to-one or being onto. So if a function is one-to-one, it means that each x goes to exactly one y. And I think that the easiest way to think about this is by looking at the mappings. So I have a diagram down here that will help you place these in your minds. So one-to-one functions are also sometimes called injective functions, but typically I'll call them one-to-one because it is more straightforward. So with a one-to-one function, it means that each x, so if this mapping shows us the x is this set here on the left and the y's are this element, or excuse me, the y's are this set on the right, each x is going to go to exactly one y. So each arrow, each element in the domain is going to have an arrow that goes to exactly one element in the range, okay? So we notice that this B goes to 1, this C goes to 2, and this D goes to 5. So none of those arrows are going to the same number. So this would be a one-to-one function. Okay. This concept of one-to-one and onto, I will say that it is a bit complicated. Okay, so if you leave this and you're just totally confused, that is okay. You are not alone. We are not going to work a ton with this idea, but as you continue your mathematical career, you will continue with these ideas, especially if you study math or engineering in college. If a function is onto, that is sometimes called a surjective function, each y goes to an x. Not necessarily just one x, but each y, so each element, so if we look over here, each element in the range has an arrow going to it. So 1, 2, and 3 all have arrows going to them, so this would be an onto function. The only time that we would see like a function that is not onto is if we had some random element. So say we had, a 4 or maybe a 5 in this range, and there's no arrows going to 4 or 5. This function would not be onto because it has some extra elements floating around in the range that do not have a domain that it's mapped to, okay? And so if a function meets both of these requirements, if it's one-to-one and it's onto, if it's injective and it's surjective, then we call it bijective, which is where each x goes to exactly one y and each y goes to exactly one x. So we see this, this perfect matching where every element in the domain goes to every element in the range. Okay, so a couple examples. State the domain and range of the relation, then determine whether it is a function. If it is a function, determine if it is one-to-one, onto, both, or neither. So the domain we're going to write in set builder notation. Here we see -6, -5, comma, -3, comma, -1, comma, 6. Close our squiggly brackets. And then for our range, we're going to look at the y's in each of those ordered pairs. We see -1, -9, -7, and 7. I do not need to write this -9 again because I already wrote it once. Is this a function? So I'm going to look and see, do my x's repeat at all? No, they do not. So we have a function on our hands. So if it is a function, now we want to think about, is it one-to-one? Is it onto? So for if something is one-to-one, we want to look and see, does each x go to exactly one y? 6 goes to -1. Okay, 6 has a buddy, -5 has a buddy, -3 has a buddy, -1 has a buddy, and 6 has a buddy. So this would be considered a one-to-one function. Is this function onto? Is this function onto? The question we're asking ourselves is, do we have any y's that don't have x's that match them? No. All of our y's, we have 1, we have -9, all of these y's, they have an x with them because we're looking at ordered pairs. So typically with any sort of function that is giving us ordered pairs, the x and y's are already matched with each other. So our function is going to be onto. All right, this example, we have a table example. Let's take a look at the domain. The domain, we're going to list out our x's, 2, comma, -1, comma, -2. That's it. Everything else, there's another -1 and another 2, but they repeat. So our range, we have all the elements that are our y's, -2, -1, 0, 1, comma, 2. Is this a function? No, it is not. We see we have our 2's repeat, our x values repeat. So this is not a function. So since it is not a function, we don't have to worry about if it's one-to-one or if it's onto, because it's not a function. So it's impossible for it to be a one-to-one or onto. It's a moot point. There's no point in asking that question if it's not a function. Other idea related to functions, another way we can categorize them is discrete or continuous. So the best way to think about this is visually, which is why I've included a couple diagrams for you. A discrete function is where the graph has disconnected points. So if you notice, we have some clusters of points here and there, but there's no line connecting them. They're just, they're just points. That would be a discrete function. Versus continuous, a continuous function has, or continuous relation, depending on if it's a function, it's where a smooth curve connects the points. So if something's continuous, you should be able to start drawing it with your pencil and then keep going through the entire graph without having to pick it up. Okay, so let's bring it all together. We're going to graph a relation here. Let me see if I can make this able to be seen. All right, so we're going to graph 1/2 x minus 3 and determine the domain and range. So let me see if I can get us some axes. That would probably be the easiest thing, to have some axes. That would be great. So these are my y-axis, this is my x-axis, and now we're going to graph. So this is an equation that is in slope-intercept form. So I can go down to my y-intercept, which is -3, and then I can use that point to generate additional points. So using that slope, I can go up 1 over 2. Up 1 over 2, or rise over run, keep going, keep going, keep going. And then eventually we will reach a point where we have enough points to connect all of them. I didn't connect it right there, but pretend that it is connected. List our domain. So if we think about our domain, what possible values of x are here? This is a continuous relation. It goes on forever and ever in both directions. So any number on the x-axis could be plugged in. So our domain is going to be all real numbers. In interval notation, we represent that as -infinity, comma, infinity, with parentheses around it. Same thing with our range. Our range goes on forever and ever. Is this a function? Since we have a graph, we can ask if this passes the vertical line test. Meaning, is there any spot where the coordinates are being touched? Like two spots on a vertical line? No, so we do have a function. Is this function one-to-one? Meaning, does each x go to exactly one y? Yes. When we have a graph, we can ask ourselves if something is one-to-one by using the horizontal line test, which is the same thing as the vertical line test, except it's just horizontal. So picture this horizontal line, if it were moving up and down, if there were ever a spot where it was being touched twice, it would not be one-to-one. So since this is good to go, we do have a one-to-one function here. And then is this onto? Do we have any y's that don't have any buddies? No, so we do have an onto function. And this is continuous because it is a line. A lot of information. See if you can take a look at the practice and let me know what questions you have.